Today we have lesson 5.2, relationship between sine and cosine. Again, getting a little bit more into the trigonometric part. This is the classwork that you should be looking at in front of you. If you don't have it, pause the video and go get a copy from the pile. But this is what we're going to be doing today. Another page, front and back. And make sure you're taking notes on that stuff. But what I want to get to now is a slide. So today we have the relationship between sine and cosine. So here's your warm-up. I want you to um, find the sine and cosine of the given angle. So for the first one, find the sine and cosine of 67. Second one, find the sine and cosine of 23. And then just basically compare your answers. What do you notice and why? So pause the video, take a few minutes to do that, and resume the video after everybody's ready. All right, so if you did the sine of 67 degrees, you'd find that the sine of 67 is going to be x. So we have our sine opposite over hypotenuse, x over z. And then if you did the cosine of 67, you would have found it would be adjacent over hypotenuse, so y over z. Similarly, if you did the sine of 23, you would have found that same y over z, which was like the cosine of this guy over here. And then if you did the cosine of 23, you would have found that it was x over z, which is just like the sine of 67. So what do you notice and why? You should have probably said something along the lines of, well, sine of 67 is exactly the same thing as cosine cosine of 23. It was x over z. And similarly, cosine of 67 is the same thing as sine of 23. Which is y over z. Now you notice that 67 and 23 add to not one, but they add to 90 degrees. So there's definitely a relationship. I actually could have given you the 23 degrees in the same angle, in the same triangle, and just said, what do you notice about that? And what you're going to notice is the sine, obviously these two angles are going to add up to 90. The whole thing adds up to 180, right? But sine of this angle is the cosine of this angle, and the sine of this angle is the cosine of this angle. That's a relationship between sine and cosine, which we'll be getting into today. So here's a big table, and if you can't see it, that's okay, but these highlighted ones are important, and the labels are important. So here's the degree measure of an angle, and the sine of its angle, the cosine, and the tangent of the angle. So here we have basically a degree of 5 if you can't read it. And you can see it matches with a degree of 85, but under the cosine. So we have a degree of 5 for an angle, and its sine is the same thing as a cosine for an angle of 85 degrees. Similarly, we have a 10-degree angle, a sine, that matches an 80-degree angle's cosine. The yellow, we have a 23-degree angle. This is what we did in the last problem, right? We have the sine of a 23-degree angle, which matches what? The cosine of a 67-degree angle. Here we have the sine of a 33-degree angle, which matches what? The cosine of a 57-degree angle. The other one down here, the sine of a 45 degrees matches its cosine of 45 degrees as well. So what does that all mean? Well, from the table, I already made these conclusions, right? Sine of 5 is equal to cosine of 85. Sine 10, cosine 80, right? All of these numbers, 5 and 85, 10 and 80, 23, 67, 33, 57, and 45 and 45, they all add up to that 90 degrees. So what can we conclude? The sine, this is our theta symbol, which I said we would talk about. We didn't get in the last one, but sine theta, right? The sine of the angle is equal to the cosine of 90 minus the angle. So here, for example, sine of 33 is equal to cosine of 90 minus 33, which is 57, right? Sine of 5 is equal to cosine of 90 minus 5, which is 85. So how does that work? And again, I kind of explained this, but if the angles are complementary, which just means they add up to 90 degrees, then the sine of the angle is equal to the cosine of 90 subtracted by that same exact angle. That's basically what that means. So example was the one that we did in the warm-up. The sine of 67 equals the cosine of 23. In the warm-up, I think they were both x over z. But that's what basically that slide means. And what else does it really mean? This is more or less the same thing, but just simplifying it either. So the sine, in this case, we have A, B, C. I couldn't find the script for that one. So we have A, B, C, right? Angle A, angle B, angle C. The sine of A is going to equal the cosine of B. And it kind of relates to this same exact stuff. Um, Here we have sine of an angle equals cosine of 90 minus the angle. Well, since angles are complementary, right, 90 minus this angle in a right triangle is going to be basically the other angle. You're going to ignore the 90-degree angle, right? This is our 90 degrees. Should probably put a box in there, but we have basically the sine of A is equal to the cosine of 90 minus A. Well, 90 minus A is angle B because you know these two are going to add up to 90. And likewise, right, we could have said the sine of B is also equal to cosine of A, right? It works both ways. So I want you to prove, do it on your own real quick, prove sine A equals cosine B on your calculator. So do sine 45, cosine 45. Do sine of 60 with a cosine of, sine of 30 with a cosine of 60, and sine 88 with a cosine of 2. And just do it on your calculator. So plug in those degree measures on your calculator. Again, make sure you're in degree mode. But do those on your calculator. Make sure you get the same decimals. Now, normally when you find the decimals, you want to keep 4 decimal points. And then after that, do a 90, a sine of 90 and a cosine of 0, and then try and put into words why this would never actually happen in a triangle. Pretty easy for that one. So pause the video, do that real quick, take a couple minutes, and then restart. All right, so hopefully you restarted now. The 45, 45 we actually did in the table, but if you found sine of 45, you'd find it was about 0.7071, as was the cosine of 45. Right, sine of 30 should have gotten you 0.5, as was the cosine of 60 at 0.5. Sine of 88, you should have had 0.9993, and the cosine of 5, believe it or not, is 0.9993. And now when you do 90 and 0, the sine of 90 is 1. And the cosine of 0 is also 1. So that does still work, but you wouldn't see this in a triangle because you're not going to have a degree measure of 0 in a triangle, or else it's not going to be a triangle. There's no angle there if it's an angle of 0. So that's why that would never occur. All right, so next we have rewriting the other trig functions as sine and cosine. Sorry. And basically what we have here for this slide is cosecant equals 1 over sine. Why? And we kind of did this the other day, but how does it really work is basically just that. We can kind of remove this. Cosecant is the reciprocal of sine, which is the same thing as hypotenuse over opposite. So again, we had done this in the other class, so this should be more review, but 1 over sine, which we think of as cosecant if it's really reciprocal, 1 over opposite over hypotenuse, which we can reduce to just hypotenuse over opposite. Again, a little bit more review, but just want you getting comfortable working with, I want you to recognize cosecant as hypotenuse over opposite, but I also want you to recognize it this way too. And basically what we're doing is we want to rewrite all of these functions, all of these other, so we have sine and cosine, but we want to rewrite the other 4 functions as functions of sine and cosine. So secant, right? Well, we can think of secant as 1 over cosine, right? And then we just rewrote it as a cosine only. Secant is reciprocal of cosine, same as hypotenuse over adjacent. So if you think of secant as hypotenuse over adjacent, you can also think of it this way. Again, rewriting a function as a cosine. Even tangent, you can think of as sine over cosine. And this is a big one. You want to know this. It's big on the homework. It's big on the activity. So tan theta equals sine theta over cosine theta. And how does that one work? Well, break down sine and break down cosine by itself. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So basically, the hypotenuses are going to cancel. You could think of multiplying hypotenuse over adjacent. So opposite over hypotenuse times hypotenuse over adjacent, right? Instead of dividing by adjacent over hypotenuse, multiply by the reciprocal or hypotenuse over adjacent. But I mean, really, what you're going to get and that's kind of what I did here, actually. Sorry, I didn't see that. So opposite over hypotenuse multiplied by hypotenuse over adjacent, right? Instead of dividing, we just multiply by the reciprocal. And hypotenuse and hypotenuse is going to cancel, and you just get opposite over adjacent, which is tan, right? So basically, what I'm trying to say to you is sine over cosine is the same thing as tan. So we can rewrite sine theta over cosine theta as tan theta. So again, rewriting the other functions, the other ratios, as sine and cosine only. And obviously, cotangent is 1 over tangent, so that's going to be, I'll explain why in this one, but that's going to be cosine theta over sine theta, just like tangent was sine over cosine, cotangent is cosine over sine. They're reciprocal functions, so you'd think the reciprocal here is going to be this one right here. So why does that one work? Again, cotangent is the reciprocal of tan, so it's the same as adjacent over opposite. So basically, adjacent over opposite might how you think of cotangent or 1 over tan, which is the same thing as this. So on your own, I kind of did it for this one. This is what I want you to do. So this one right here, I broke down sine and cosine and did some multiplication and ended up with back to tan. So I want you to prove that cotangent is the same as cosine over sine using the same way. So break up cosine and break up sine into what they actually are, opposite and adjacents, and hypotenuse. And take a minute to do that one. Really, this one shouldn't take too long, so pause the video and then restart it in a little bit. All right, so maybe restart it. It's going to be, you can kind of follow along with your work, but cosine is adjacent over hypotenuse, and sine is opposite over hypotenuse. So the hypotenuse are going to cancel on both. You would have adjacent over hypotenuse times hypotenuse over opposite, multiplying by the reciprocal. And basically what that's going to be, I probably should have put in a visual on here, but you should have it in front of you if you did it right. You're going to end up with just an adjacent over hypotenuse, and that's exactly what cotangent is. So you basically just proved that cosine theta over sine theta is the same thing as cotangent of theta. So moving on, we're going to try a couple, or a few. So we have our triangle ABC right here, B being our 90-degree angle. So we have sine A plus cosine C. Well, if we think about it, right, these are our two acute angles. So sine A plus cosine C is the same thing as saying 2 sine A or 2 cosine C. And how did we really get that? Well, if we remember, sine A, right, one acute angle, is the same thing as cosine B. So when you get problems like this, you want to rewrite everything as one letter. So sine A plus cosine C, you could say, well, how can I rewrite cosine C? Well, hey, wait a second. Since A and C are complementary, sine A and cosine C are the exact same thing. So you could basically say, well, that's just going to be 2 sine A's, right? 1 sine A plus 1 sine A is 2 sine A. Or you could have rewritten sine A as a cosine C, because again, they're complementary. You could do it that way and get 2 cosine C. Number 2 is a little bit more difficult. We have sine A plus cosine C over cosine A. And what's that going to be? It's going to be 2 tan A. And that's going to be, I'll explain it in a little bit, but basically, we're going to end up with sine A plus cosine C, which is the exact same one from here. That's going to give us 2 sine A. So we're going to have on the numerator here is 2 sine A over cosine A. And again, if you remember from that last slide, tangent is the same thing as sine over cosine. So we're going to have 2 sine A over cosine A. That's just 2 tangent of A, right? Because the sine over the cos is going to give you, sine over cosine is going to give you a tangent. So it's going to be 2 tangent A. Now this one here, sorry, I should have put this back up there. I did mention it. But when solving for these, try and make sure your letters change to 1. So you only want to work with one letter and leave your answer in terms of one letter or angle. I mean, the letters represent the angle.